The next type of positive displacement pump we'll be taking a look at are vane pumps, of which there are two flavors: unbalanced vane pumps and balanced vane pumps. We'll take a look at the specifics of the differences between these two later on in the lecture, but for now, let's focus on the operating principle and the geometry. Between unbalanced and balanced vane pumps, the general operating principles are the same as the previous types of positive displacement pumps we've taken a look at. That is to say, these pumps operate by taking a package of fluid, right, sealed off in these triangles, right, a volume of fluid from the inlet, and pushing it around to the outlet at a higher pressure. The reason we call these vane pumps are because they use a mechanism which we refer to as vanes. These are small barriers affixed to springs, which are attached to this center rotor here, and these vanes can extend or retract as the vane pump spins around. Notice how at the inlet here, the vanes are fully extended, and as our rotor spins around, the vanes are pushed in towards the center of our rotor, which constricts the volume of fluid inside of these chambers. This increases their pressure and forces them out at the outlet. Now, an important metric to take note of here is something called eccentricity, shown here in this green line. The eccentricity is just a measurement, right, measured in inches or meters, and it's an offset from the center of our cam ring off to the side where the rotor actually spins about. Again, notice this isn't spinning in the very center of our pump, it's slightly offset, and that distance that it's offset by is known as the eccentricity. Take note of this value as it is extremely important in terms of how the pump will actually behave. Let's look at some math regarding vane pumps. First, let's talk about maximum values. We can calculate the maximum eccentricity, that is this distance here, right? The distance that the center of the rotor and the center of the chassis are offset by taking the diameter of the cam ring in inches or meters and subtracting it by the diameter of the rotor in also inches and meters, and then dividing that by 2. This gives us our maximum eccentricity value, which again is just going to be a measurement, right? Inches, meters, some unit of length. We can then use that to calculate the maximum volumetric displacement. That is to say, the maximum amount of volume that these chambers can have filled with fluid. This is done by taking pi over 4, multiplying it by the, again, diameter of the cam ring plus the diameter of the rotor, then multiplying that by 2 times the maximum eccentricity, which we calculated up here, and finally multiplying it by the width of the rotor, or L. Now that we can calculate our maximum turns, let's take a look at why we actually call this a maximum value instead. Specifically, this will be for unbalanced vane pumps. Unbalanced vane pumps actually allow you to change this eccentricity on the fly using something like a lever, right? We can reduce the eccentricity or increase the eccentricity in order to change the characteristics of our pump. Specifically, if we change the eccentricity value, we change VD, or the volumetric displacement. That is, the amount of fluid that our pump is displacing. This allows us to adjust the flow rate of the pump. We can see that the formula is very similar to our maximum value, right? Taking pi over 4, multiplying that by the diameter of the cam ring and the diameter of the rotor, the diameter of the cam ring plus the diameter of the rotor, times the eccentricity at that specific setting, times the width of the rotor. Here's just a quick recap for all 3 of these equations, as well as what each of the variables actually is. Again, unbalanced vane pumps allow us to adjust this eccentricity value, right? Increasing the eccentricity will increase the flow rate. Decreasing the eccentricity will decrease the flow rate. When the pressure at the outlet increases, the pump will have the benefit of reducing eccentricity, which lowers flow rates, which prevents pressure from rising. This is similar to how dynamic displacement pumps work. That is to say, as the outlet pressure increases, we can let that affect the eccentricity, right? We can have this thing automatically reduce its eccentricity to reduce the flow rate, which ultimately reduces the pressure on the system. However, the downside to this variable displacement is that by having a high pressure on the right and a low pressure on the left, we create unnecessary forces inside of the pump. Balanced vane pumps fix this by instead having an inlet pressure on both the top and the bottom, and the outlet pressure be on the left or right. That is to say, while there is still technically only one outlet and one inlet port, internally, that is inside the pump, there are two channels where this pressure can flow, thereby balancing the forces inside the pump, which allows for lower amounts of degradation and higher efficiencies. The downside of this, however, is that the eccentricity cannot be adjusted, meaning our flow rate for balanced vane pumps is fixed. Let's go ahead and do a quick example here. We're told that a vane pump is to have a volumetric displacement of 5 cubic inches. It has a rotor diameter of 2 inches, a camring diameter of 3 inches, and a vane width of 2 inches. We are asked what the eccentricity should be set to, which we remember is labeled with E. Going through and labeling my units, right, we have E is our target value. Just do a little question mark there. We know that our volumetric displacement, denoted by VD, is equal to 5 cubic inches. We are noted or told that our diameter of our rotor is 2 inches, and we are also told that the diameter of the camring is 3 inches. Let's, again, as we usually do, take a look at our toolbox and see which equation we can use. Here we have our max eccentricity, but that isn't really going to help us. Same spiel here, right? We have a max volumetric displacement, but we don't necessarily want the maximum. We're looking for whatever eccentricity will produce a specific volumetric displacement. And looking at the different values here, our diameters, our length, our volumetric displacement, and the eccentricity, which is what we want, are all present in this equation. So that's the equation I'm going to choose to use. Let's come over here and write out my equation. So, maybe we'll do it over here. VD is equal to pi over 4 multiplied by the diameter of the camring plus the diameter of the rotor multiplied by the eccentricity multiplied by the length, or the width, excuse me. Again, don't know why they're using the L here, but I'd like to stay consistent with the book, so we'll do what the book does. And I also forgot to note that down over here, so I'll just take a quick note. L, or the width, is 2 inches. And we actually have almost all the variables we need in order to solve this equation. We know our volumetric displacement is going to be 5. Maybe I'll just write the units down here. Cubic inches is equal to pi over 4. The diameter of the camring is 3 inches. The diameter of the rotor is 2. inches. We don't quite know the eccentricity yet, so I'll just leave that as E. And our width is 2 inches. And as we can see, we only have one unknown here, right? Our E. So let's go ahead and simplify this equation first, just to make the math a little easier for us to do, right? These two add together to get 5, so we get 5 pi over 4 times E times 2. We can factor our 2 to make this guy 2. So we finally get 5 equals 5 pi over 2 times E. We can then multiply both sides by 2 over 5 pi times, scooch this guy over, times 2 over 5 pi, which finally, right, and we can see the 5's factor here, these guys factor, and this leaves us with the eccentricity being equal to 2 divided by pi, right, which would be roughly 2 over 3.14, right, which would be, well, I don't have my calculator on me, and we can let my calculator do that later. So whatever 2 over about 3.14 is. Again, we can think about the inches, or the units, and I kind of gave you guys the answer there, but remembering back here to our diagram, the eccentricity is a distance, right, a unit of length, and since we've been working in inches, we know that E will be pi over 2 inches. By setting our eccentricity to pi over 2 inches, 2 over pi inches, we will get a flow rate of 5 cubic inches in this pump. Or I should say a volumetric displacement of 5 cubic inches for this pump. The final type of positive displacement pump that we'll take a look at are piston pumps. Piston pumps operate on a similar principle to the previous positive displacement pumps. That is to say, they suck fluid up into specific volumes, move that volume somewhere else, that is the outlet, and then push it back out. However, instead of utilizing gears or vanes, piston pumps use, well, pistons. Right? You may notice that this looks very similar to the actuators or the cylinders we've been using. Right? The key difference here is that where in a cylinder or actuator, like the ones you've used in labs, the energy in the hydraulic fluid is converted to mechanical or linear motion, versus in the case of a piston pump, we utilize mechanical motion to move the fluid. Right? The energy goes from the mechanical domain over to the hydraulic domain. Piston pumps operate by first retracting the piston, which creates a vacuum and sucks the fluid up at the inlet, then extending back out to push the fluid out at the outlet port. This pulling and pushing motion is created by a slightly tilted axial shaft that, as it spins, pushes and retracts these piston rods in and out of these chambers. The neat thing about these piston pumps, specifically the axial design of piston pumps, is that by adjusting the piston stroke, that is, by adjusting the angle that our piston is up and down, we can change the amount of fluid that is sucked up into the pistons and forced back out at the outlet. Notice here at the maximum angle, right, when we tilt this piston head by a lot, our piston will retract by a substantial amount. Now, as we reduce this angle here, right, as we lower this angle, the piston no longer retracts and extends as much as it did before, meaning we can adjust our volumetric flow rate. It is important to note that if our piston is perfectly aligned along the axis of our pump, the pistons here no longer extend or retract, meaning there's no suction or no pushing, and this pump essentially is just a carousel for the fluid to go around. It doesn't really pump the fluid at all, just kind of moves it in a circle in a gentle way. This makes the axial design for piston pumps a positive displacement pump, but we also call this a variable displacement pump. That is to say, the amount of fluid that is sucked up and deposited can be adjusted, but it is still a positive displacement pump because it does this chambering of the fluid here, right? It is in these distinct packets that are sucked up and delivered. The radial design, on the other hand, cannot be adjusted. It is still a positive displacement pump, but it is a fixed displacement pump as well, a positive fixed displacement pump, right? Positive because we have our chambers that segment off the fluids, but it's fixed displacement because we can't really adjust the flow rate of this pump, right? Notice in this design, we have no way of adjusting this angle that we had in this previous axial design. It is set at a fixed angle, meaning that we cannot really change the stoke of our piston, right? We can't change how far this moves back and forth, meaning we will always displace the same amount or volume of fluid.